In this video, I will be going over the electricity project for academic physics. In this video, I'll be talking about the expectations for each slide. I will also be going over an example set of calculations for the last couple slides because that seems to be where we're running into the most trouble. So our first slide is the title slide. Make sure you check the project description to see what we're looking for on the title slide. It's an easy set of points. Second slide, you need to find or record an electrostatics demo. So there are tons of different electrostatics demos already available on YouTube. I'm pretty sure if you literally type in the phrase electrostatics demo video into the YouTube search, it will come up with a couple good ones. The third slide is where we're first starting to get into the actual meat and potatoes of the project. You have to explain the physics in the video. So explain what is going on in the video, why it's happening, and how you know it's happening. The fourth slide, you need to draw or find a circuit with 3 resistors. I'm seeing quite a few people use the PhET simulation to draw their circuit diagram. If you are doing that, just keep in mind that light bulbs are not necessary. Light bulbs themselves are resistors. I've seen a couple people put in 3 resistors and 3 light bulbs. That's a total of 6 resistor elements, which is fine. Just means you're going to have to do more work. So 3 resistors. You need to have 1 battery and 1 switch. Please note, when you put the switch in, it cannot be in a position to disconnect the entire circuit. That means it cannot be directly after or before the battery. It also cannot be directly after or before a resistor that is in series with the battery. You also need to have a parallel component and a series component. I'm going to give you an example. Oh, and all of these things have to be labeled with numbers. Again, you can use the PhET simulation. In the bottom right-hand corner, there's a battery symbol and then a symbol that looks like this. I would click on the symbol that looks like this. That way you get the schematic diagram and it looks a little bit cleaner. So I'm going to start off with a battery, which is connected in series to a resistor. I know it's in series because my wire goes from the battery into the resistor. Again, I'm not allowed to put a switch here. I'm then going to have the wire connect up to what we call a junction point and split, because I need to include a parallel component. And in order for me to have a parallel component, I have to have a split. On this side, I have a 2 ohm resistor. On this side, I'm going to have another 2 ohm resistor. Now I need to bring these wires back together, and I'm going to give a more complicated circuit diagram just so we can see different kinds of ways of connecting these. Again, you only need 3 resistors. This is going to be connected in series, so this entire parallel component is going to be connected in series with another parallel component. On this branch of the parallel, I'm going to have 2 resistors. These resistors are in series with one another because my current flows from one into the next. On this side, I'm going to put my switch. Again, I have to have a switch somewhere in my circuit for it to count. I'm putting it on one of the branches of the parallel circuit. That way it is not directly in series with my power supply, with my battery. Easiest way to make sure you're not screwing up the switch placement. Start at your battery. Trace your circuit. If you can trace a circuit, starting at the battery, going all the way through without touching the switch, your switch is not going to completely disconnect your circuit. And I'm going to just finish off this diagram real quick. And just for fun, I'm going to put another resistor right here. This one's going to be 4 ohms. The one up top I'm going to label 2 ohms. The battery I'm going to label 12 volts. So here's my diagram. I have a battery. I have at least 3 resistors. I have a series component. Here's a series component. I also have parallel components. There's parallel. There's parallel. So I'm satisfying all the requirements of the diagram. Now we need to move on to the 5th slide. This is where it really gets difficult. We have to do calculations for when the switch is closed. And on the next slide, we need to do calculations for when the switch is open. If you need to do multiple slides for the closed circuit calculations and multiple slides for the open circuit calculations, do that. Do whatever you need. The first thing we're going to calculate is the equivalent resistance. Calculating the equivalent resistance is different for parallel and for series, and I'm seeing a lot of people confusing the two. So I'm going to just focus on my resistors. I'm going to draw a quick little sketch to remind myself of what my circuit looks like. Since the switch is closed, I'm going to just replace the switch with a wire and pretend like the switch isn't really there, because that's what happens when you close a switch. It connects the circuit, the current can flow through without any interruptions. Now I'm going to track through what happens. I'm going through one resistor and then I split. A split is a parallel component, so I'm going to deal with that first because it's more complicated. Here we have the equivalent resistance equation for a parallel is 1 over Req equals 1 over the first resistor, this one right here is 2 ohms, plus 1 over the second resistor, this one is 2 ohms. So I have 1/2 plus 1/2 is 2 halves, also known as 1. So 1 over the equivalent resistance is equal to 1. Therefore, Req equals 1 ohm. Now I'm going to go down here. My current reconnects, and it splits again. So I have another parallel component. I have 1 over Req equals 1 over, but on this branch, I don't just have one resistor, I have 2. And in fact, the current is going from one resistor into the next. That is a series component. So I need to deal with that next. The equivalent resistance for series components is just the sum of the components. So Req equals 1 plus 3. So Req equals 4. So this whole branch here is 4 ohms. This other branch is also 4 ohms. So I have 1 over 4 plus 1 over 4 equals 2 over 4. Got to remember that equals 1 over the equivalent resistance. Therefore, the equivalent resistance equals 4 over 2. I have to invert. Parallel is weird. It is the sum of the, it is the inverse of the sum of the inverses. You have to do 2 inverses, and that equals 2 ohms. Do not try to do it quickly. Always write it out. I would recommend when you're picking your values for your circuit, you try to pick numbers that have a common denominator, or that you can find a common denominator. Don't do a 3 and a 7. Instead do a 2 and a 4, or a 2 and a 6. Something where you could get that common denominator so you can add up fractions like you did back in middle school. So now this diagram up top is getting kind of messy, so I'm going to rewrite it. I have not touched this 2 ohm resistor at the top. But instead of this parallel component, I can now replace it with this 1 ohm resistor. Instead of this parallel component, I can replace it with a 2 ohm resistor. Now when I look at this diagram, I see a 2 to a 1 to a 2. My current is going straight through them, so it is in series. Req equals 2 plus 1 plus 2 is 5 ohms. Req equals 5 ohms. Again, this example is more complicated than the one you have to do. You only need to do 3 resistors. I did, 6 resistors. The next thing you have to do is something that I saw a lot of people misinterpret: current calculations. You need to calculate not the total current. So you should not be doing V equals IR, where V total, which is the battery, equals I total times REQ, which you just calculated. That would only tell you the current that is running straight out of the battery. You need to find the current through each resistor. For this, I strongly recommend you go back over Kirchhoff, but I'm going to do it here. It can take a while. It's going to take me a while because I have 6 resistors. Keep that in mind. If you just have 3 resistors, it should take you a lot less time than it's going to take me. I'm also going over this very, very slowly. So we have our 12-volt battery into a 2 ohm resistor, splitting to go into 2 ohm resistors, coming back together, only to split again and go into a 4 ohm resistor, a 1 ohm, and a 3 ohm. First thing you should do for Kirchhoff is figure out what currents you have. Coming out of the battery, I have a current that goes into this junction point. I'm going to call that current I1, just because I stands for current and 1 it's my first current that I'm talking about. But anytime we see a junction, the current will split. And we have I2 and I3. Anytime you have a junction, you should write an equation. What is going into that junction? I1. What is coming out of that junction? I2 and I3. This is a statement of the law of conservation of mass. If something goes into a point, the same stuff has to come out. The amount of stuff going in has to equal the amount of stuff going out. Those two come back together into another junction. Well, that current there, first off, is not doing anything because there's no resistor. But I could call that current whatever I want. I'm going to call it I1 again. Because if 1 became 2 and 3, then when 2 and 3 come back together, they're going to remake 1. Then we have another split, another junction. So I'm going to label this I4 and I5. You might be wondering, why don't you label it I2 and I3 again? I1 became I2 and I3 earlier. The difference is this, what's going on here is different than what was going on up there. So I don't know for sure if those currents are going to be the same. So I'm not going to assume. So here we have I1 equals I4 plus I5. Then down at the bottom, they're going to reform and create a current again. Well, if I4 and if I1 became 4 and 5, then 4 and 5 coming back together are going to remake I1, which is going to flow up and around into the battery. We call those our junction rules for Kirchhoff. Now we need to do our loop rules. There are lots of different loops you can do. A loop is just a closed path that you are going to trace. So I tend to like to start with the battery and follow around an entire wire segment until I get back around to the battery. So I'm going to just follow it around and around and around. My first loop that I like to do is always the inside. So I'm going to start with my 12-volt battery. The thing about loop rules is they have to equal 0. This is just a statement that any energy I get from the battery has to be used up by the resistors. So my battery is going to give me energy. I'm coming out the positive side of the battery, so I have positive 12. As I go through, I use up that energy by going down with the current. So I'm going this way with the current. I have minus 2I1. I'm going with the current here. I have minus 2I2. Again, I'm going on the inside path, so I'm following this path as I go through. I know this is getting messy up top. This branch here is 1I4 and 3I4. So again, let me just redraw the path I followed. Started at the battery, went through a resistor, went through another resistor, went through 2 resistors, and back around to the battery. I came out the positive side of the battery, so it's positive 12. I'm going downstream. I'm going with the current in all of these segments, so they're all negative. Now, if I have 0 equals a positive number minus a whole bunch of things, I can rewrite that to only have positives by moving all those negatives to the other side. And I have 2I1 plus 2I2 plus 4I4. Because I can combine 1I4 and 3I4 into 4I4 equals 12. I can simplify that if I want to, but I'm just going to leave it as is. Next, I'm going to do the outside loop. So the outside loop would be my battery into a resistor, into another resistor, into another resistor, and back around to the battery. 0 equals, came out the positive end of the battery, positive 12 volts. Went downstream through this resistor, minus 2I1. Went downstream through this resistor, minus 2I3. Went downstream with this resistor, minus 4I5. I can rewrite this with the negatives all becoming positives on the other side. And I get 12 equals 2I1 plus 2I3 plus 4I5. I could also do a loop up in the top branch. So up at the top I have these resistors up here. I could make a loop inside of here. I could go downstream through this resistor. I'm going to call this top parallel. So I'm going downstream through the resistor on the right, minus 2I3, but I'm going upstream through the resistor on the left. So instead of it being negative, when you go upstream, it is positive. I always think of this in terms of streams, in terms of rivers. When I go with the current, I'm going downstream as negative. When I go against the current, I'm going upstream as positive. 2I3 equals 2I2. Well, if 2I3 equals 2I2, then I know that I3 has to equal I2. That's going to be useful. I can also do one for the bottom parallel. I'm not going to redraw this just because I'm running out of space at the bottom. I have 0 equals negative 4I5 because I'm going downstream on the right, plus 1I4 plus 3I4 because I'm going upstream on the left. 4I4 equals 4I5. I4 equals I5. That's a lot of work, and I'm not done yet. I don't have numbers yet, but I'm really close to having those numbers. Remember, I'm doing 6 resistors, not 3. It takes more time to do 6 than it does to do 3. When you're doing your loops, it doesn't matter if you go clockwise or counterclockwise. I always go through my loops clockwise just because if I'm always following that clockwise pattern, it's easier for me to track in my math what's going on. It's really obnoxious when one loop is clockwise and the other loop is counterclockwise. So I'm going to copy over some of the equations from the other page. I1 equals I2 plus I3. This was our first junction rule. Also had I1 equals I4 plus I5. That was our second junction rule. I2 equals I3. That was from our third loop rule at the bottom. I4 equals I5. That was from our fourth loop rule at the bottom. From this, I can take I2 equals I3 and substitute it in here and get I1 equals I2 plus I2, because I3 and I2 are the same. Therefore, I1 equals 2I2. Anywhere I see I5, I can replace it with I4. Well, I see an I5 right there. I1 equals I4 plus I4. I1 equals 2I4. When you're solving for things with Kirchhoff, it's a good idea to use junction rules, but you also always have to use at least one loop, just because that loop is what gives you the battery for V equals IR. So I'm going to pick the first loop, because why not? 12 equals 2I1 plus 2I2 plus 4I4. That's my first loop that I wrote. Anywhere I see I2, I can look up here. Well, 2I2 equals I1. I see a 2I2 there. So I can replace it with I1. 12 equals 2I1 plus I1. If I see 2I4, I can replace it with I1, but I don't see 2I4. I see 4I4, which is double that. So I can write 2I1 equals 4I4, which means everywhere I see a 4I4, I can replace it with a 2I1. 2I1. Now I have an equation here that only has one variable in it. I can combine like terms on the right. 12 equals 5I1. I can solve for I1 by dividing, and I get I1 equals 2.4 amps. That is one of my currents. I have 5 currents. I need to solve for the rest. So I'm going to take this and plug it back in up there. And I get 2.4 amps equals 2I4. Therefore, I4 equals 1.2 amps. Well, if I4 is 1.2 amps, I5 is also 1.2 amps. I can also take this and plug it in here. And wouldn't you know it, I2 and I3 will also be equal to 1.2 amps. Those are my 5 different currents for all of my resistors. Typically, we need to find a current for each resistor. So if I have 6 resistors, I need 6 currents. However, 2 of my resistors, the 1 and the 3, since they're in series with each other, they're both going to have that current I4. So this I4 applies for the 1 ohm and the 3 ohm. Okay. Next slide. We have to do the open calculations. When you open the switch, any resistor that shares a current with the switch is ignored. So if I were to redraw my schematic, there's my schematic. This switch here is sharing a current with this resistor. So this entire segment here will not work anymore. If that entire segment won't work anymore, I don't have to worry about it. So instead, my circuit looks So in order to find the REQ, I'm going to take these two and combine them. Well, I already combined them before. That parallel segment we said was 1 ohm. So I can redraw this entire schematic to only have the stuff that I need. I have the resistor up top. I can replace these 2 on the side with this 1 ohm resistor there. I can ignore the side with the switch. Now I have all 4 of these resistors connected in series. My current goes from 1 to the next. So REQ equals 2 plus 1 plus 1 plus 3. REQ equals 7 ohms. As far as doing Kirchhoff, it's now a little bit simpler because I have fewer currents. Whatever, I'm going to call this I1 again. It splits into I2 and I3, but it rejoins and becomes I1. Remember, it can't go down the path across if we open that switch. There's no current that can flow there. So I now am down to just I1, I2, and I3. So it's going to be a much simpler calculation for Kirchhoff. I hope this has helped clarify how to do things. Please keep in mind point distributions. If you're really confused on calculating the currents, you can make your best effort and still get a decent grade on the final project. That being said, If you want to check your answers, I would strongly recommend you use the FET simulation, plug in the values you're using, and you can actually put ammeters and voltmeters in the circuit to test what the current is flowing at different points, so that you can know for sure if you're right or wrong. If you got any questions, let me know. Hope this helped.